Recording in progress.
Okay, so first some announcements. Remember that homework 3 is due today at 10. Homework 4 will be out today as well. And as most of you already realized, exam 1 grades are up on Gradescope. They were released last Wednesday, so you have until this Thursday kind of resolve any regret requests. The TS should follow on them. If they don't, you can ping them again. Okay. And just some statistics about the exam. As I said on the post, the scores were, as expected, pretty good. So the mean was 20, which is like 80%. Median is 20.75, 83%. Max is 25, maybe around 10 to 15 students got the max. And around 73% of the students scored more than 18. Okay. And just to put this in context, something that I mentioned back in first class, typically the number of A's is maybe between, should be, somewhere between 35 to 40%. B's is typically in the same range. And, I got several questions from people that, okay, these numbers mean median are high, somehow I scored less in this exam. But again, there's still a lot of points left in the course, right? You have 2 more midterms and these are non-cumulative. So you have plenty of time to catch up if you just focus on what's coming up as well. Okay. Any questions about the exam and kind of, the grading mechanisms? Exam and solutions are also up on the website. So you can also kind of understand if there's anything missing. Okay. All right, so if there are no questions about the exam, we can now go on to what we were talking about last class. So last class, we defined this fundamental notion of Turing machines. We saw some examples, and then we started looking at, why is this toy model or seemingly toyish model really a good model, or why is it interesting, right? And then we kind of stated this church-turing thesis, started comparing Turing machines versus all of our modern programming languages. And today what we'll do is kind of expand on these 2 points first. How does Turing machine compare to modern machines? And it will lead to what the book aptly calls HOCAEIP, or have our cake and eat it too principle. We'll see how to use it. And then this will lead up to 2 of the most important ideas in computer science. Okay, so kind of, greatest hits of 20th century science today. So pay attention. Okay. And hopefully we'll get to both of them just in this one lecture. All right. Okay, so just a quick recap. So last class, so a Turing machine, right? A Turing machine is completely determined by the transition function. It's a finite description of something that does computation on all inputs, right? So you have some case states, let's say, some alphabet, sigma, and is completely determined by this transition function, okay, which takes a state name, an alphabet symbol name, and outputs what the next state should be. What are you going to write where the head is? And then what's the movement of the head? Right, so this was our complete description of the Turing machine. Left, right, state, or halt. Okay. And a Turing machine, when we have this way, defines a function, right? So a Turing machine M defines, let's say the output of a Turing machine is what's on the tape until the head when halted. Okay. So when the machine halts at that stage, we declare the output. Okay, whatever is written on the tape from the start of the tape to where the current head is pointing, that's going to be the output. Okay. So defined this way, we can think of the Turing machine as something which takes an input, which we're still thinking of binary strings, and gives an output, which can now be something over the alphabet, right? Because you might be writing something over there, but that's not too important. It's like a technicality from the formalization that we're using, right? And then, given our discussion of the church-turing thesis, we led to this sort of very boastful definition that a function f, which takes binary strings as input and binary strings as output, is computable, okay, by a computer, right? If there exists a Turing machine M such that f of x equals m of x for all inputs x. Okay, so we're not saying that the machine is computable by a Turing machine anymore. We're just saying it is computable because we have this confidence behind the model of computation of Turing machines, right? And this came from two things. Some things we can prove, some things you just take it for granted. And this is what a theorem I stated, for every Python program. P, there is a Turing machine M such that P of x equals M of x for all x. Okay. So for any Python program you can write, there is a corresponding machine M, which when given the same input produces the same output as the Python program. Okay. In some sense, this seems like a very simple extension of DFAs, but it's as powerful as any of your modern programming languages. Okay. This is something that we can prove, but we did not prove in this class. All right. And some of you also proposed some extensions of Turing machines, right? So recall that when we defined Turing machine, it was kind of you have a single head which is moving left or right, right? And then we have many, many possible extensions. Turing machines, like maybe allow multiple heads. It takes a little bit of more notation to kind of define this formally. Just as we define a single tape, single head Turing machine, you just have to change some things in this transition function. You'll look at one of those things in the homework, but the essential idea is kind of the same, right? But I don't want to cover all of this extensively because we really want to focus on the bigger picture. Allow multiple heads, allow multiple tapes, and so on. Okay. And the sort of amazing thing about Turing machines is its robustness, in the sense that no matter what extensions you can think of, at the end of the day, you can actually show that all of these are implementable, or let's say can be simulated by a let me put it in quotes, by our simple Turing machine. Okay, the plain vanilla Turing machine, the single tape, single head that just moves one step at a time, that can capture all of these things. All right. So these are all things that we saw, kind of last class. Any questions about these concepts? I'm reviewing this because we're going to exploit this critically in the discussions from here on. Okay. All right. So, and finally, we had the church-turing thesis, right? Yeah, this is like a law of nature. We can't really prove it globally, but for anything that people kind of conceive of, we have been able to prove it. Every function that is computable by a physical means, is computable by a Turing machine. Okay. So the equivalence Python, the equivalence between this multiple heads and multiple tapes, these are formally defined well enough that we can actually prove it. But there's a more general statement that we believe is true, is that any function that you can implement with physical means, meaning in current known laws of physics, is actually implementable by a Turing machine. If you have a quantum computer, yes, you can simulate that using a Turing machine. Relativistic computation, you can simulate that using a Turing machine, and so on. Okay, and these are all things that have been verified, but the global thing is just to be taken as a law of nature, at least until it gets proven otherwise. All right, and this discussion leads to a very nice win-win scenario for us. Okay, and it's going to be very useful. I mean, it is very useful in much of computer science, and particularly for what we're going to do next. Right, so what do I mean? Okay, so maybe let me expand it out once. I don't know how good you are with your acronyms. Have our cake and eat. Oops. Two. Okay. So what's the have our cake part here? So the have our cake part is that to show something is computable, I can use any powerful modern programming language I want. Okay, you can write a Python program for multiplication, but then I already have this amazing theorem which tells me that there's a Turing machine, right? So if I ask you to write it, okay, is there a Turing machine that can do division? You'll say yes, because here's a Python program which can do it. Okay, is there a Turing machine that can find shortest path from graphs? Yes, here's a Python program which can do it. Hence, there is a Turing machine. Okay, so that's our have our cake part. You don't have to go ahead and design the Turing machine from scratch every time. So to show something is computable, you can use a high-level programming language. Okay. So this allows us to kind of focus on the main ideas instead of like going into the nitty-gritty details of designing Turing machines and so on. Once we have this powerful theorem that any program can be simulated by a Turing machine. Okay. Any questions about this part? So that's the first win for us. Okay. What's the second win? where is the ET2 part come from? The ET2 part comes from the following. To show something is uncomputable, we just, again, I'll put it. We just have to show that Turing machines cannot do it. Okay. If tomorrow someone comes and says, okay, here's a problem that I want to solve, and ask you, okay, is there a program in the most complicated programming language you can imagine, let's say Perl or in Python or something very messy that can do it? Can say, okay, a Turing machine cannot do it, so no matter what language you're going to use, it's not going to do it. Okay. Some sense we are using, seems like a cheat, right? To show something is possible, we're allowed to use the most powerful thing that we can imagine. To show something is impossible, we just have to kind of show that the weakest form, or seemingly the weakest form, cannot do it. Okay. So that's why we are having our cake and eating it too. Any questions? No? It's like, you're playing a chess competition, and to win, you get to pick the best player. And if you're choosing an opponent, you get to choose the worst player. Right? Okay. All right. So we will use this to demonstrate, as a convenient tool for proving two critical theorems, right? And again, there's two parts to it. I'll state them just as a punchline, and then we'll try and dig into what these things mean, okay? So the first theorem, which is called universality, right, says that there is a single Turing machine that can simulate all Turing machines. Okay. And this is a single Turing machine. It's called a universal Turing machine. Okay, so in other words, if you had to go ahead and somehow implement a physical device that kind of really does the Turing machine, okay, I'm going to hard code these transition functions into a robot which is going to do it. Which machine would you pick? I would pick the single universal Turing machine. Okay. So a little bit like what we saw in Boolean circuits, there was a universal circuit which could evaluate all circuits. But I think this is way beyond that in terms of circularity, because there you cheated a little bit. The circuit, your universal circuit, would be bigger than the circuits it was taking. Right? But here it's a single program. Maybe it has 25 states, 4 alphabet. It can simulate a Turing machine with 1 million, 1 million states, no matter what alphabet. Like much bigger things. Okay.
Was what you showed us last time with the site that with the Turing machine, was that a universal?
No. So no, I think it's slightly different. That is important, but not in this context, because we're going to focus on a fixed size thing. Good question. All right, so we'll dig into its implications in a little bit. Okay. All right. The second part is the ET2 thing. Okay. So we'll prove this universality by having our cake. And then we're going to eat it. I actually should have got cake to complete the metaphor. Next year,
You throw cake at people.
I wouldn't dare. I'm sure it's going to backfire next year. Okay, so there are functions that are uncomputable. Okay, so far everything you've seen is like some functions we could compute, some functions, regular functions, some functions are not regular, but then you can compute by a simple algorithm and so on. But we'll actually see that there are some functions that no computer, however complicated, however big a program you can take, how much ever time you can take. It's not about time. I give you an unbounded amount of time. You want exponential time? Go ahead. You want doubly exponential time? Go ahead. You want a tower of exponential? Go ahead. You still cannot compute the answer to these things. Okay, so that's the import of the second statement here. All right, so that's what we're going to go towards. Okay, so that's much to do about what's coming up. So let's see kind of the blueprint behind how we are going to do this. All right, and the basic idea is something that we sort of saw back when we discussed Boolean circuits, right? So there also we had like a two parts. We said, okay, there is a universal evaluator circuit, and then we also said there are functions which cannot be computed, right? And the core behind both of these things was, anyone remember? The idea that data can be taken as code, or code can be taken as data, right? So that's going to be critical here too. So the fact that programs, or in our case, Turing machines, can be taken as input, right? So code as data. Okay, so that's something that we're going to expand on, just as we did then, and that has the two implications. Right, so universality and uncomputability. Many differences from the circuit world, but I think there's some analogy between the two, right? So they also say we can take code as data, we can take circuits as input. So we got universality, and then instead of uncomputability, we got a size lower bound. Okay. So that's where we are headed to next. Okay. So let's talk about this part first, universality. And so what does it mean to have a universal Turing machine? So the object that you might be most familiar with that corresponds to universal Turing machines are, any guesses? Like something that you have used maybe many, many times. Laptops, or something even more specific within it. Yeah? Even more specific. No. Well, think a little bit like software. Something a little, yeah. Maybe, but I was actually looking for a compiler. Right? A compiler is a universal Python machine, right? What does a Python interpreter or compiler do? It can take any Python program, take any input for that program, and tell you what's the result of running that program, right? So you should really think of universal Turing machines as the conceptual equivalence of compilers, or it's actually compiler plus executor. So both wrapped into the same. Okay, we kind of break it up because we want debugging facilities and so on. But really, you could just imagine there is something, some Python program, or some program. It doesn't matter what it's implemented in, which takes a Python program and input, and then just tells you the answer of that. Okay, and that's exactly what we want in the context of universal Turing machines. But the goal is we want this program itself to be a Turing machine. Okay, so that's a hard thing to wrap your head around, right? It's like saying I can write a Python compiler in Python.
You can.
You can.
That's how the C compiler would work.
Yes, we're going to see why. Okay, so what do you want? So that machine, the Turing machine, should take another machine M as input, and input for that machine, right? Is taking the pair of them, and it's going to simulate the machine on the input and tell you the answer. Okay.
So its output will be the machine on X.
Yeah, it's just like compiler, right? Imagine this is your Python, the C compiler, and with the runtime executor takes the program, takes an input string, and tells you the answer. That's it. Okay, that's what we're going to talk about next. All right, any questions? Okay. So to make sense of this statement, we need to first talk about how we are going to represent Turing machines, right? Because the way we defined it, every input is just a binary string, right? And this is something kind of seems silly when you think about it abstractly, but also something that always happens on your machines. Whenever you execute a program, what is the compiler taking as input? It is taking the raw text file which contains a program as input, right? For the compiler or executor, the input is just a sequence of strings. That's it. Doesn't know it's a program or anything. Takes a text file as input, does some tokenizing and so on, and then runs it, right? So the input is just the text file. In the same way, right? So we have to represent these as binary strings. Okay. And in the programming world, this is equivalent to saying programs are just text files.
So are you saying the Turing machine itself is going to be represented as a binary string as well?
Yeah, exactly. I mean, this is something that actually happens every time you run a compiler, right? It takes a binary string as input and then simulates a program. Okay. It's not something that we are just doing for theoretical reasons. It's actually something that happens. And there's an interesting anecdote about it that I'll tell you in a bit. Okay. So what is our goal then? Our goal is to first talk about how can we represent Turing machines, how can we encode Turing machines so that we can give it as input to another machine, right? How is your program being passed to the interpreter program? Okay. And again, there are tons of conventions you could use. As long as you fix one, it doesn't matter what specific encoding or representation you choose. Okay. So we'll just pick one, at least something that is simple enough, but clearly not optimal, but kind of helps our discussion go ahead. Okay. So recall that a Turing machine is entirely described by its transition function. Okay. So a Turing machine is completely described by this transition function, right? And you can think of the transition function as really like a table, right? It tells you, okay, take a state I, a symbol A, And then, you jump to state J, rewrite to some symbol, move the head somewhere. Okay? You can think of it as a list of these sort of instructions, right? If you recall the Turing machine simulator code that we had in the last class in the demos, they had a very similar thing. The first line was just the two things. The second line was what's going to happen afterward. Okay. Any questions about this? So we had to just fix some encoding for how to represent this transition function. So let's say the number of states is K, number of alphabet symbols is L. Okay, so you can imagine the alphabet. I'm just going to number it for convenience as A0, A1 through AL minus. So you have K states, L symbols in your alphabet. All right. And each transition is of the form, I have in state I get the alphabet symbol A. I have to jump to state J, write down alphabet B there, and take an action A. Okay, so these are the sequence of instructions that you would have. Okay, so if you imagine writing this as a big table, it would be something like, okay, so 1, 2, 3, 4, 5. Right, so it's like, I have state 0, A0, then I go to some other state, maybe A17, maybe some other symbol A10, move the head to the right. 0, symbol A1, go to state 10, write some other thing here, move the head to the left, and so on. Okay? So how can I represent this transition function delta? How can we represent delta as a 0, 1 star? Any suggestions? Like, how can I encode this entire program as a single binary string? We've done it, a couple of times already. Just, we don't have to go into the gory details, but just a hint would be good enough. Any suggestions? Well, we know how to sort of use and reuse representations, right? So first, I'll say I'm going to write down the number of states the machine has, okay? Then I'll write down the number of symbols in my alphabet, okay? And then I'll just start listing out all of these things. Okay, it's kind of very brute force-ish representation, right? I'll say, state 0, symbol A0, jump to state whatever, write whatever, move the head in some way. Okay, so that's a 5-tuple, collection of 5 entities: state, symbol, action, right? And then I can just put all of these as a single list.
Yes.
Okay, I'm just going through the entire thing. I have a sequence of these 5 tuples, which tell me what the transitions are supposed to be. And I just wrote down all of them in a single list. Okay. That's not me. Okay. All right. But is the representation clear? Again, we've done it many times. I'm just kind of slightly rushing through this because it's not particularly important what representation we choose. Okay, this level of detail for us. So how many tuples? How many 5 tuples will we have? Any guesses? How many 5 tuples will we have? Yeah. Exactly, right? So it's just K times L. Because we have K states and L symbols. You know, for every state and every possible symbol, I have to tell you where you're going to go next, right? And each tuple has, you know, you can think of it really as 5 integers.
It's 5 integers. It's 5 integers.
Please mute yourself. Unfortunately, if I mute everybody, then when I disconnect, it becomes problematic. Okay. So each 5 tuple has 5 integers, right? You know, we have a starting state I, a symbol A. Again, we're indexing them, right? You know, A0, A1 through A-1. The specific name of the symbol doesn't matter. It just matters that, you know, you're consistent with what you're using as symbol 0, what you're using as symbol 1, and so on. Okay. And then you have to write down what's the new state, what's the new symbol you're going to write, and what action you're going to take. Okay. All right. So and so each 5 tuple can be represented as a 0-1 star string. Right, so we know how to get representations of tuples from individual things, and here is just integers. So we group them together to get a representation for the 5 tuple. And from there, we go to representation for the list of 5 tuples can be represented as a 0-1 star string. Okay, because we know, recall, we can compose okay. Any questions about this? Right. So just to kind of iterate. So we have the Turing machine, which is the transition function, gets first coded up as a list of these things, right? One, two, three, four, 5. Okay, so we have a sequence of 5 tuples, everything. This entire thing is encoded as a single binary string. Okay. Again, we're doing what we've done many times before, which is If I have an encoding for individual elements, then I can get an encoding for tuples, then I can get an encoding for tuples of tuples, and that would be it. All right. Any questions about this? Okay. And it's not important for us, but we can just do some amount of just to kind of sanity check. Let's do some bookkeeping. And the length of the encoding will be dash. Okay, so how long is this encoding going to be? Unlike our discussion for circuits, this length of the encoding is not at all important, but just, you know, you can count it easily. All right. So we have K times L many tuples. Each tuple has 5 integers. Okay, and the integers take values from, you know, 0 through k or 0 through l minus 1, right? 0 through k minus 1 corresponding to the states, and 0 through l minus 1 corresponding to the alphabet symbols, right? So we can represent this with something like log k plus log l bits, right? So each integer is less than or equal to the max of k comma l. Okay. As I said, we're not really interested in splitting hairs here. Just the most significant bit is that, okay, to encode the state, it's a number from 0 through k minus 1. How many bits would I need? Log k. To encode the alphabet symbol, how many bits would I need? Log l, right? I have 2 states, you know, and, you know, 2 states, 2 alphabet, and something LR. You know, this is just like a single. There are only 4 options, and maybe you only need 2 bits or something, but doesn't matter, right? The precise things don't matter. Roughly something like this. Okay. And how many such tuples do we have? K times L. Okay. So the rough length of the encoding is something like this. So if I have a Turing machine with K states and L symbols, then I can encode it as a binary string with these many of this, you know, this length. Order of K times L is log K plus log L. Okay. And the length is not important for us. What is important is the punchline. We've done what we've done several times before to conclude the following. A Turing machine M can be represented as a binary string. Okay. All right. And for convenience, this is something, the reason we'll do this will be a little bit clearer. If you think of, so for a machine M, we will let So I'm just going to use a little bit of shorthand, makes the things that we're going to write clearer. For any machine M, right? If I put these 2 angle brackets, that's meant to denote the binary string that corresponds to that machine, right? It's really like saying that, okay, here's the handle for the text file which contains your program. and then passing around this text file to another program or doing whatever with it. But it's a text file. There's no sort of semantic meaning to it until you read into the text file. It could be Hamlet for all we know, or it could be the code to, it could be a compiler itself, right? It could be anything. It's a text file. It's a binary string, and we're just passing that around. Okay? So that's the main thing to take away. There's a single binary string which represents the machine, and we fix the convention once and for all. So there's a one-to-one correspondence. All right? So you can think of this like, maybe there's a universe of all Turing machines. We have all kinds of machines here. Maybe some machine is doing, how do you draw a machine? Okay, different laptops. Okay, so every machine is being mapped to a binary string. And this is going somewhere here, this is going somewhere here, this is going somewhere here. They're all going to different binary strings, right? Each program has its own unique representation. Okay. And there's one more notational convention we will use. This makes certain things easier. So as defined, this gives us a one-to-one mapping, right? For every machine, we are getting a binary string, but not all binary strings would be valid Turing machines, right? It's the same thing as saying, okay, every program gives me a text file, but not every text file is a valid program that can be executed, okay? But always saying, okay, if it's a valid program, it makes more sense to do something like this. If a string, let's say alpha in 0, 1 star is not a valid program, to a trivial Turing machine that always outputs it. Okay. I'm kind of, completing the picture just so that we don't have to carry this notation every time saying, okay, I have a string, maybe it's not a valid program, then what do I do, right? You're not going to have that issue because if it's a string that does not correspond to a valid program under original encoding, I'm just going to assign it to a dummy program, which will always output 0. Okay, it doesn't look at this input, just output 0. Okay. Any question about this? Yeah.
Why is this important? Because this makes it no longer one-to-one.
It's one-to-one. It is still one-to-one. Remember, one-to-one is from left to right.
But now, don't you have the Turing machine that always outputs 0 mapping to many strings?
No. So again, remember, so that's a good question. So imagine these are all the points that do not have a corresponding thing on the back, right? And I'm saying just assign them, just interpret them as corresponding to a dummy Turing machine. Yeah. So the mapping is well defined for the original Turing machines that we have. And maybe there is the Turing machine that outputs 0, right? It went somewhere here. And whenever I see an input string, what am I supposed to do, right? When we define the universal Turing machine, it's going to take an object on the right-hand side as input. Okay, if you're, imagine if you give, let's say, a Shakespeare novel to your Python compiler, what would it say? It's a compiling error, right? So now I'm saying instead of compiling error, just output something like 0 every time. Okay, so just a notational convention. It's not changing the fact that every machine that is properly defined corresponds to a unique string. Okay, instead of saying compilation error, we're just saying output 0. That's it. Okay. All right. So now we come to what makes universality possible, right? We can define a function eval which takes a binary string as input. Okay. Okay, which takes a binary string as input and gives an output which is either well-defined, or recall that Turing machines had this, we had this perpendicular notation to say it went into an infinite loop, right? So that could happen too. So the evaluator function should take the machine and the input to the machine and should output m of x. Okay, so this is a function we're defining now. It's well defined because it takes a binary string here, checks if it corresponds to one of these machines, runs that machine on this input, and returns this. Yeah?
How do we get this thing that's computing it to understand like the very first code that we ever give it? Because if we're giving it a binary string, it's just a language, it doesn't have any encoding or doesn't understand encoding. How do we?
Right. So we have fixed the encoding in our mind, right? Now the machine has to do, we don't know how to do it. I'm just describing what functionality I want, right? We don't know how I'm going to actually implement a machine to do this. Okay. So this is my dream. I want something which does this. I give it a binary string. It breaks it up exactly as we want, as into the pieces of the Turing machine, and runs the Turing machine, and then gives me the output, right? So I want something which does the compilation. Like if you know compilers, then you take the text file, break it up into tokens, break it up into loops, whatever, and then you have to run it. So there are all these steps which are wrapped into this one functionality I want. Okay, this is the function I want. I haven't, or we don't know whether it's actually computable or realizable. Okay. Any questions about this? All right. Okay, so now we can state Turing's first amazing theorem that showed this in 1936. Eval is computable. Okay. So there exists a Turing machine U such that U of m comma x is actually equal to eval m comma x for all inputs. We're saying that this eval function that I want, my dream interpreter, exists. There is some single Turing machine which can compute the eval function. There is some single Turing machine which can break up the binary string into the relevant pieces so that it decodes the exact Turing machine that you want, simulates it, and tells me the answer.
Turing called the Turing machine?
No. Yeah, it's he did call them Turing machines. He wasn't that presumptuous, although he could have been. But yeah, okay. So let's take a 5-minute break, and when we come back, we'll discuss a little bit about the implications of it, and then see and take a few steps towards proving it. All right? Okay. Okay, so we are going to prove this theorem by our celebrated Haber-Cake principle. Okay, so, but what this is saying is that there exists a Turing machine that can compile plus execute, do both Turing machines. Okay, so to understand the importance of this, I would say first kind of step away from this binary representation part. Just imagine that there's some representation. It's not at all important what representation you choose. Okay, so the fact that we did this encoding, tuples and so on, that's really like weeds. We don't care about that so much. Doesn't matter what representation you use. You can use anything that makes sense as long as it's one-to-one, it will be fine. Okay. And just to kind of, get a sense of first, so this is Turing, by the way. This result came out in 1936. He was actually a phenomenal long distance runner who just fell shy of making England's Olympic team back then. And he thought that his job was so stressful that the only thing he could do to get out of the stress was to run, and run really hard. And if you know his history, he's also kind of a very enigmatic and tragic figure. There's a movie which, I mean, it's good, not as great, but I encourage people to watch it anyway. And the tragedy is that he actually committed suicide due to harassment by the British government. And it's kind of a sad story. And there are all sorts of cartoons, and XKCD has many, many things on Turing machines. This talks about one particular fantasy of eating candy paper as a Turing machine would. I guess if you work as a hacker long enough, you start dreaming like Turing machines. You start crossing the road like a Turing machine, maybe. Okay. And so we are going to see a different proof of the Turing machine, but this is from his paper, which is almost like, let's say it's, I guess, November 12th, 1936. So 86 years ago. And he wrote down, it is possible to invent a single machine which can be used to compute any computable sequence, which for him was any computable function. If the machine you supplied with a tape on the beginning of which is written the standard description of some computing machine M, then you will compute the same thing as M. Okay. And the next section is devoted to giving the complete table for this universal Turing machine, right? So the table was something like this. He did not have a Haber-Cake principle. He did not have Python or anything like that. So what he did was he introduced the idea of multiple head Turing machines back then, showed that they can be simulated by a single tape Turing machine, use the multiple tape head Turing machines to build the universal simulator, and then got back his universality theorem. Okay. At the end, it had like some, not humongous, but still a non-trivial number of states, like 100 or something like that. Okay. And finally, I should say, how simple can the universal Turing machine has been a contest. People have gone to great lengths to write better and better universal Turing machines, and not just in Turing machine as a language, but you can ask the same thing for other languages. And here's a famous example, famous in the sense of the history of programming languages. This is from a paper by John McCarthy introducing the Lisp programming language. And this is the Lisp function, which is a Lisp interpreter. Okay. Yeah. So it just takes, it is a universal Lisp machine in the sense that it takes a Lisp program, runs it on the input, and gives you the answer. Okay. So this is the meta-circular evaluator. So we call it meta-circular because there's really no limit in what you can give it as input. You can give it the same interpreter again. Okay, it's going to do something new. What if I give the interpreter and the program as input? It will give you what the interpreter would on the program, right? And so in John McCarthy, defined the Lisp programming language and gave a Lisp function that evaluates an arbitrary Lisp program. It's very short, remarkably. And he introduced mainly as an illustration that Lisp is more elegant. I mean, this Lisp universal function is more elegant than the universal Turing machines that people had at that point. Okay. And his graduate student, Steve Russell, thought that this should not just be a theoretical exercise and implemented it in machine code. So it can be implemented. So he wanted to write an interpreter for Lisp. And the way he wrote the interpreter was actually take this function, this universal one, and code it up on the machine language, IBM 704 machine code, whatever that machine was. Okay. And that's how you had the first sort of interpreted language. Okay, it started out from this exercise of writing a universal Turing machine in some language, then you can code it out. So if you had to build a computer, just go ahead and take Turing's 1936 paper, implement that as a device, and then you're done. Okay. He thought he was confusing theory with practice. This eval is intended for reading, not for computing. How often do you see that, right? And as far as meta-circular evaluators go, there is another sort of nerdy contest where you can write the shortest possible program, which will print itself. So when you execute the program, it should print itself. It's not as easy as saying, okay, write down the text file as part of the text within the program, because then it's no longer the same. Okay. And lots of fun games. We'll talk about some of these things later. Okay. Just a little bit of history. And okay, so this is one more thing. So Turing already realized the importance of universal Turing machines. Okay. So the importance of the universal machine is clear. We do not need to have an infinite or infinity of different machines doing different jobs. The engineering problem of producing various machines for various jobs is replaced by the office work of programming the universal machine. I guess he rightfully calls software programming or software engineering as office work as opposed to maybe field work or using punch cards, but that's what he thought was possible. Okay. So let's get back to here. So those are some of the implications of this universality result, right? And how are we going to prove it? Any guesses? Not the way Turing did. We're not going to write down a multi-head Turing machine which can do this and then convert it to a single-head Turing machine. But what we're going to do is use something more modular, right? So have our cake proof. So what would it mean to prove this using or have our cake principle? Any guesses?
What's the hamartic principle again?
We get to choose a programming language to show that something is computable. Yeah. Right in Python, right? We know that every Python program has a Turing machine. So if I give you a Python program of 10 lines, there is some Turing machine, fixed Turing machine. Maybe it has 100 states, maybe it has 1000 states, but there is a Turing machine which exactly does what the Python program is supposed to, right? So we get to pick our programming language. So let me pick the Python language. And this is written up in the textbook. As a Python program, it's extremely simple to write down a universal Turing machine. Okay? If I ask you to write a compiler for Python in Python, it's going to be nasty, right? But if I ask you to write a simulator of a Turing machine, it's very easy because of how simple the logic of the machine is, right? You just have a single state that you have to move. All right. So this is our Python implementation of eval. So it takes the eval function, takes the description of the machine and the input that you want the machine to run on as its own inputs, right? And again, the binary encoding part is not important. So let's imagine that the transition table is already been split up as some kind of table, right? List of things. Okay. So how do we simulate a Turing machine? I'm just going to start with the tape being empty plus the string x, right? So what is the Turing machine supposed to do, right? What are we supposed to do? We have to simulate what the transitions as dictated by delta do when I initialize the tape as x0, x1, so on, maybe x n minus 1, where n is the length. There's empty symbols afterward. The head is pointing here. And I have to simulate the transitions of delta on this array. Okay. You're not interested in using Turing machine. You get to use Python. So how would I do it? I'd say initialize an array which contains these things. My head is pointing to the starting state, which is 0. My starting state is just 0. And then I just go through each step. So I look up what the transition table is telling me to do when I'm in state S, the current state, what I read at the current head. It's going to ask me to jump to a new state, update the tape in some way, and take an action. Okay. If the action says halt, you just halt. If the action says move left, then I change my head position. If the action says move right, then I change my head position one step to the right. Okay. And sometimes if I'm writing it in Python, I'm here, and then I have to increase the move. It asks me to move one step to the right. I just append this empty symbol there. Okay, that's a quirk of Python, right? You can't deal with infinite arrays, but you can allocate them dynamically. So if I'm reaching the end, then I just increase it by one more symbol. Okay. Any questions about this? Let's see, how many lines is it? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 lines within Python to simulate a Turing machine. Okay. And regarding the output, I guess there's a typo here. This should not be this. It should be, I'll tape. Okay, so there's a small typo here. And once we end up simulating the machine, we have to do the output, and the output is everything until where the head position is. So you start from index 0, and you just keep appending until you get to the head position, which is I. Okay? And you return the output. Okay? So we have a simple Python program that can do a Turing machine, that can simulate a Turing machine. So it can compute the eval function. And by the theorem that we stated but did not prove, by our have-or-take principle, we know that there is a Turing machine which does the same thing as this eval function. Yeah? Are we? Yeah, we should. So this should be less than or equal to. Okay. Any questions? Okay, so I mean, it might seem like a cheat, but it's a cheat only because we are using something powerful, right? Which was our have or take part. So we saw a Python program to compute eval. Okay, so there is a simple Python program, maybe about 15 to 20 lines, which computes eval. So this implies that there is a Turing machine. Okay, so let me write it differently. We know for every program P, there is a corresponding Turing machine. That computes P, right? So it implies that there is a Turing machine that computes eval. Okay. And if you did want to go through this powerful theorem, it's again not like it's a huge advantage to use this theorem, but it minimizes and minimizes the work and emphasizes the central concept, which is that you can do this sort of simulation without too much difficulty on a Turing machine. Okay. I mean, obviously, Turing did not have Python programming language. What he did, as I said, was write down actual instructions for how to do this sort of decoding of the binary string into pieces corresponding to the instructions and then execute them. Okay. Any questions? So that's the power of our principle, right? We get to use our favorite programming language to come up with an algorithm or come up with a Turing machine. All right. Okay. So that's one way to prove universality. But now let's think of what are the implications of it. Okay. And this is something maybe we touched on already, which is that one implication of universality is that we have general purpose computers. Right? All we need is a single Turing machine, which is this universal Turing machine, and we can run any Turing machine on it, right? Which is kind of the foundation of general purpose computing. There's a single computer which can simulate any other program. Back in Turing's day, people designed specialized hardware. I mean, we kind of do that now for efficiency reasons, like GPUs and TPUs and so on. But that's very different from having a machine which could just add numbers, having a machine which could just multiply numbers. And people were actually building physical devices, which all that they could do was add, all that they could do was multiply, all that they could do was add up some trigonometric series. Okay, they had physical devices which could, process some trigonometric functions. That's it, nothing else. Okay, Turing came along and introduced this idea that you can have a single machine which can simulate all machines and showed how to do it. Okay, and in fact, so there exists universal Turing machines with something like 25 states and alphabet, our standard alphabet. That's it. So just 25 states, nothing else. Yeah.
Why don't you put the star on this set as opposed to like 0, 1 star?
Oh, because this is the alphabet, right? So the what you write on would have the star, but what is it made of? Each individual entry, it's one of these 4 things. Okay. So, I mean, obviously this is not something we saw, right? Because we said, okay, we have a Python program and then we go to a Turing machine, which can have huge loss. Turing's universal Turing machine itself had something like, I think, around 150 states. He didn't write down everything, but if you look at the paper, you can see it starts writing down the table of all the case analysis and so on. Kind of gets pretty detailed. See, these are all the instructions for the universal Turing machine that he had. Okay. But people have optimized it a lot. And at the very least, we know that there is a universal Turing machine with only 25 states and these many things. So to understand kind of, the mind-bending nature here, just imagine how long would it be if I had to describe this machine, right? So there are 25 states and 4 symbols. To write down the entire description would be something like, maybe 100 5 tuples, right? So there's a sequence of 500 integers, which is as powerful as any computer. Okay, in terms of description length. So this universal Turing machine is completely described by something like 500 numbers. Okay, and it can compile and execute any other program that you give it. Okay, it's like telling you that, okay, there's a Python interpreter which just takes 500 numbers to describe. That's not possible just because there's a lot of complexity in the language, which allows us to use a lot of syntactic sugar. But for Turing machines, we reduce the complexity of the model so much so that the simulation becomes much easier. Okay. All right. Any questions about this? It's just like simple description of a universal Turing machine. The reason we're not writing it down is even though it's only 500 numbers, kind of a very, very intricate case analysis based construction. Okay. Again, we are not interested in how short this is. We're interested in the fact that there exists such a thing. Okay. Yeah. And the other thing to take away from Turing's construction is this idea of a meta-circular evaluator. Okay, which is like an interpreter or compiler. And something we always see, like if you think of GCC, this is a compiler for C, it is written in C. How does this make sense? You know, what does it mean to say I write a compiler for C within C? What is going to run GCC itself if you already don't have a compiler for C? It seems so circular that should not be possible, right? So the reason it's actually possible and it's not like you're cheating is that when you say GCC is written in C, there's some kind of bootstrapping that happens. So basically you implement something like a Turing machine first, and then use that to add functionalities one after the other. Like there's layers and layers of things, okay? It's like peeling an onion. You implement a basic version of C, which does not have pointers, let's say. And then you use that version to implement a version which has pointers. And then you use that to implement a version which has, you know, maybe classes and so on. Okay, so you kind of build things layer by layer. At the bottom, essentially, is something like a universal Turing machine. Okay, that's where the recursion bottoms up. All right. And finally, there's also this important takeaway that universality transcends the specific model. Okay, what do I mean by this? So we saw that there's a universal Turing machine which can, there's a single Turing machine which can evaluate all Turing machines, right? In the same way, there is a single Python program that can run all Python programs. Okay, so this is telling me that there is actually a Python interpreter or compiler for Python, which is written in Python. Okay, the same for Java, same for anything like that. Okay, and it's not just like, you know, you can use the same language, you can crisscross. Okay, there exists a compiler plus executor for Java programs. Okay, so maybe let me write it slightly differently. There exists a Python program that compiles and executes Java programs. Okay, so there's a single Python program which can take any Java code as input and return you the output. Okay, there's a single Java program which can simulate any Python program, and so on and so forth. All right, so this notion of universality actually is not specific to Turing machines. In fact, it's hardest to see for Turing machines because of how we implement it. But once you have this higher functionalities, things start becoming a little bit more involved, more easier. Okay, and there's also this notion of Turing complete languages. Okay, so these are all programming languages that can simulate a universal Turing machine. Okay. So there are very strange languages, which turn out to be actually just as powerful as any other language. Okay, we think of some languages as more powerful than others, but they're really more powerful only in terms of syntactic sugar, right? They make writing programs easier because they help us think better, write shorter code, write cleaner code, which is very important. But at the end of the day, if you had to go to actually, designing a device, all of them are kind of almost the same, right? There's some strange languages which turn out to be Turing complete. Like for instance, LaTeX is Turing complete. Okay, so I can write a LaTeX program, which is just a text file, which can run and execute any Python program for me. All right, I can do the same in, somebody did it with HTML plus CSS. Okay, imagine writing a compiler for C in HTML plus CSS. It is possible. I don't know if you would do it. But the way they did it was they found a universal Turing machine. Okay, sure, how to code that functionality within HTML plus CSS. Okay, but we know the universal can do everything, so you get the power of everything once you implement the single machine. Okay, and lots of other stuff. Sometimes it really backfires when you have Turing completeness. People have exploited hacks like this in security breaches and so on, where people design certain sort of languages which are very constrained. Like, if you have a switching network, you only allow certain programs to run on it, but then people realize that they're Turing complete, so make them do all kinds of crazy stuff and so on. Okay. So Turing completeness itself is, like many examples. Okay. Any questions about what universality means and what we're discussing so far? Okay. If not, that's all I wanted to say about universality, that there's a single Turing machine which can evaluate all Turing machines. And the reason it comes about is because we can simulate, instructions using Turing machine. Okay, we can simulate a program using Turing machine. Okay. All right. So what we'll do next is to, we had our cake. Now we're going to eat it and show something else, which is that Turing machines can evaluate any Turing machine, which is great. They can simulate, they're just as powerful as any other programming language. But unfortunately, there exist uncomputable functions. Okay, so there is a function f that cannot be computed by a Turing machine. Okay, so there is a function that cannot be computed by a Turing machine. All right, and this is also proven in Turing's 1936 paper. Okay, so that paper defined the model and then talked about universality, and also that, as good as universality is, there are some functions which cannot be computed by a Turing machine. All right. And we'll kind of first give a function which seems very impractical and unimportant, which is uncomputable, because, we just want something to get started with. And then we'll see how this connects to many important things that we really, really like to solve in our applications that turn out to be impossible to solve. Okay, many of the things that have huge practical implications turn out to be impossible to solve. Okay, but what I want to do next is define what this function is. The definition is a few lines, and next class we'll talk about why this is uncomputable. But the reason I want to define it first is kind of give you some time to understand what this definition is. It's just a few lines, but I think it's sort of very circular, so kind of confusing. So just you have to kind of just play with it a little bit. So I'll call this function the toddler function. Todd, not a department's chair, but the toddler. So it takes a binary string as input, and it only has a single bit output. Okay. And what's a toddler function do? It really mimics what a toddler would do. Okay. What would a toddler do? Any guesses? Yeah. Well, something worse than that. If you're doing random, sometimes you agree with. Toddler basically does the opposite of what you want them to do, right? So the first time I taught this class was during COVID, and everybody could hear my toddler in the background. So that gave me the inspiration to call this function the toddler function. And so the punchline of this function is toddler does the opposite of what you asked them to. So what do I mean by this? Okay, as I said, I'll just define it, kind of try and get a sense of this definition. It's just a few lines, but very confusing to me at least. Okay, so suppose I give a string as input to the toddler function. Okay, I'm defining the function. I'm not defining a machine. I'm defining the functionality that I want, right? On an input, what it does is it first interprets the input as a program. A binary string corresponds to a program, to a Turing machine, right? So let's call this M, okay? So meaning I view it really as some sequence of instructions, your Python program, anything, just view it really as a blueprint, as a description, the binary encoding of the machine, of a machine, okay? And what do you mean by it does the opposite? It takes a machine and does this experiment where, just imagine, right? You have a 2-year-old who is trying to think what you would want them to think and then does the opposite, okay? Which is really what happens. Okay, so you have this machine. Just imagine what this machine would do when given this same text file as input. Okay, maybe let me not draw this picture, but say, look at the output of M when given its own description as input. Okay, so you can take any Python program, give its own code as input to the Python program. Nothing prevents you from doing that, right? Because the program can take any text file as input. I'm just giving its own code as input, right? So now it runs the program on itself and then does the opposite. Meaning, maybe let me move it around a little bit. If false and the first bit of output is 0, then output 1. Okay, and otherwise 0. Okay, so you have your text file, you have your program's code. I'm going to feed the program to itself, make it eat itself, look at the output. If the output starts with a 1, if the output starts with a 0, I'm going to say a 1. If it doesn't halt or see anything else, I'm just going to output 0. Okay, so it mimics what the program would do when given it itself as input and does the opposite. Okay, any questions about this definition? Right. So what I want you to do is kind of think about this definition until the next lecture. And what we'll show then is that this function toddler is uncomputable. Toddlers cannot be fathomed by us. Okay? We cannot compute what this function is. All right. And that's what we're going to see in the next lecture. All right. But try to understand this just seemingly silly, just 2-line definition, but there's a lot of meta computing going on in this definition. Okay. All right. I'll see you all in the next lecture on Wednesday.